All right, so now let's look at this proof. So this is a proof that we want to show that a set is uncountable. Okay, so we're going to look at the set of real numbers, prove that the set of real numbers is an uncountable set. Right? So this is there are a few ways to show this, but I'm going to explain what's called the counter-diagonalization argument. Cantor was a famous mathematician that did a lot of or started a lot of the set theory stuff. Okay, so this is Cantor's diagonalization argument. Okay, so first of all, we're going to make an assumption that we're going to look at values, real numbers, in the set 0 to 1. Okay, so we want to kind of show that this set from 0 to 1 is an uncountable set, and then generalize it to all the real numbers, and that's fairly straightforward to do. Okay, so let's look at the set of numbers, and we're going to do this by contradiction. Okay, so by contradiction assumes that this set of numbers is countable. Okay, so remember, this is real numbers, so they're going to have decimals in them. So we're going to assume that it's a countable set. So assume that 0 to 1 is a countable set. Okay, this means that we are able to list the elements, let's say x1, x2, x3, x4, ... in such a way that they are in one-to-one onto correspondence with the set of positive integers. 1, 2, 3, 4, and so on. Okay. Basically, this just says that it's like this is the first element, the second element, the third element, the fourth element. So basically, kind of this indices right here. It shows the one-to-one onto correspondence with the positive integers. So if I can list them in order, then it's a countable set. Okay. So let's look at some numbers. Let's say that I can make my numbers in the list only using 5s and 6s. Okay. So let's only use 5s and 6s. Again, sort of, we're doing this for simplicity, although these, you can see that we can generalize to numbers that are other than 5s and 6s, but this will kind of keep the argument a little bit simpler. Okay, so we're looking for real numbers from 0 to 1. Okay, so they're going to start with a 0 and a dot. And I can make them only out of 5s and 6s. So the first number could be like a 5, 5, 6, 6, 5, 6, 6, ... My second number is 0.665, 655, ... Third number, 5, 5, 5, 6, 6, 6, 5, 5. Fourth number, 6, 5, 6, 5, 6, 6, 5, 6, and so on. You can come up with any examples right here. All right. So now we're going to, so again, sort of, these are a countable set because I can list them. Right. This connects with the number 1 of the positive integers, number 2, number 3, number 4 of the positive integers. So because I can make a list, these are countable. All right. So now we're going to construct a new number. Okay. So we're going to construct a new number. So kind of in my list here, I have an infinite countable set of numbers, all made out of 5s and 6s that belong to 0 to 1. let me construct a number in this way. So I'm going to construct a number, again, in that set from 0 to 1, in such a way such that we're going to do the opposite. Okay, so we're going to look at the first number, and in the first decimal place, this has a 5. I'm going to put a 6 in here. So we're going to do the opposite. If it's a 5, put a 6. If it's a 6, put a 5. Then in the second decimal place, okay, this has a 6, I'm going to put a 5. In the third decimal place, this has a 5, I'm going to put a 6. In the fourth decimal place, this has a 5, I'm going to put a 6. Okay? So you go through each number in your list of numbers already, and you're going to flip. You're going to flip from 5 to 6 and from 6 to 5. So you form this number right here. Okay? Now, because this is different from any number on my list at a decimal place, this is actually a new number. This is not a number in my original list. Okay? Now, my assumption was that this was a set of countable numbers. That means that basically I was able to make a one-to-one correspondence with the set of positive integers. But now here's a new number, right, that I constructed that's different than all the others. So my correspondence is no longer one-to-one because I have more numbers in my list than I can count. Okay, so basically this gets me to a contradiction. All right, so now we can extend this. So basically here we show that the set of real numbers, x is real, from 0 to 1 is uncountable. Okay, but now we're going to say because the set 0 to 1 is a subset of the real numbers, then the real numbers is going to be uncountable. If a subset of it you can't count, then a bigger set has the same problem. Okay, so because 0, 1 is a subset of the real numbers, then the set of real numbers is uncountable too. Okay, so this is a neat little proof. The same idea, kind of same strategy of kind of constructing these new numbers but making it different in each decimal place from the ones you already have. It's kind of a nice and beautiful and simple one. Cantor came up with this argument. And it's a fairly famous proof in math and set theory. All right, so let's kind of switch concepts. So we're going to look at what's called the Pigeonhole Principle now. You might have heard the wording before. Some of you, I think, a lot of you have done the writing assignment in the Pigeonhole Principle. This counts from counting, probability and counting and all that stuff. But we can sort of connect it with the functions that we've talked about to kind of see how they're related. So we're going to say let f be a function from a finite set x into a finite set y. If n is bigger than or equal to 1, and the cardinality of x is bigger than this number, bigger than 1 times the cardinality of y, meaning that x has more elements than y does, then there exists an element of y that is the image under f of at least n plus 1 elements of x. In other words, if k is a positive integer and k plus 1 or more objects are placed into k boxes, then there's at least one box containing 2 or more of the objects. And the reason this is called the Pigeonhole Principle is that when people were coming up with this stuff, they kind of tried to visualize this with pigeons. So basically, if k is a positive integer, so here's like if I have k number of boxes available, kind of imagine these are pigeon houses. There's space, kind of space in a pigeon house, right? And k plus 1 or more objects are available, right? So if I have k plus 1 pigeons, so one more pigeon, then there are boxes available in their houses. then there's at least one box containing 2 or more of the objects. So if I only have k places to fit my pigeons in and one more shows up, then one box is going to contain more than one pigeon. Okay, so this is kind of the principle of the pigeonhole. So a function from a set with k plus 1 or more elements to a set of k elements is not going to be one-to-one. We could just kind of show proof with the diagram, right? So if I have my domain is set of elements 1, 2, 3, 4, dot, 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 k plus 1 elements, but I only have in my range or my codomain, I have 1, 2, 3 k spaces, okay? Then this is not going to be one-to-one because you can sort of do one-to-one correspondence. 1 goes to 1, 2 goes to 2, 3 goes to 3, 4 goes to 4, and k goes to k. But this last element right here has to go somewhere if it's a function, and it has to go to one of the spaces that are already occupied, which means you have at least one value in the codomain comes from the 2 different x's, so this is not going to be a one-to-one correspondence. Not one-to-one. So here's a couple of examples of the pigeonhole principle. So show that among any group of 367 people, there must be at least 2 with the same birthday. Okay, so if we have the domain, we are 367 people, right? So person 1, person 2, person 3, all the way to person 367, right? My codomain is the days of the year, right? So we could have January 1st, January 2nd, February 29, December 31st, right? So in the codomain, there are 366 days, different days in the year, including the February 29th. Right? So if I draw the correspondence, like one person could be born January 1st, another person could be born January 2nd, another person, right, February 29th, right? The 367th person, let's say the 366 is born December 31st. If we've used up all the possible dates, the 367th person will have to double up with one of the people, so there must be at least one match. Now here's a second example, very similar. Show that any group of 27 English words, there must be at least 2 that begin with the same letter. Okay, so the words are my domain. All right, and letters is my codomain. So the words are word 1, word 2, word 26, word 27. The letters available are A, B, C, D, X, Y, Z. All right, and there's 26 available letters in the codomain. All right, so again, you can match one word to a letter. Okay, by the time you reach the 26th word, now they don't all have to be different letters, but sort of you could have word 3 also go to B, right? But basically, the 27th word will need to this, I guess, number 3 could be your 27th word. Once you sort of already doubled up, then it's not going to be one-to-one correspondence. That would be at least to the begin with that. Okay, so that's why we're kind of looking at them. The first goes with A, the second goes with B, the third goes with E, the 26 goes with C. That 27 letters will have to double up with one of the, a word will have to double up to start with the same letters as one of the others. And the pigeonhole principle is generalized to this. Like if you have n objects that are placed into k boxes, then there is at least one box containing at least n to the k objects. This is the ceiling function, so you're rounding up. Okay. So let's look at this. What is the minimum number of students required in a discrete math class to make sure that at least 6 will receive the same grade if there are 5 possible grades, A, B, C, D, and F? Okay, so this is asking, what does this number need to be, that if I'm going to divide the students into these 5 boxes, each of them represent the grade, right, and I round it up, then at least 6 will receive the same grade. Okay? So you can see that this number has to be 26, right? So n would have to be 26, right? If n is 25, right? If you have n is 25, then you could divide and you get 5 students go into each box. But if you have an extra student, if you have 26 students, then at least one of the boxes will have to have 6 receive the same grade. Okay. All right, so this is the end of this section. Just kind of looking at property of functions in terms of injection and surjection, one-to-one and onto functions. If they have both properties, those are called bijections, and kind of just some applications of those bijections. You can show the pigeonhole principle and figure out if sets are countable or not. The next sections we're going to look at, use those properties to talk about inverse and invertible functions.